Welcome to the final day of Cosmology on the Beach. We have the final course lectures going on today, and we're going to start with Katrin Heitmann, who will give us the third part of how to simulate the universe.
Thanks very much. I renamed my talk a little bit. It was originally called The Galaxies, but we heard such nice lectures from Claudia about the galaxies, so I was scared to actually give a talk like that. So I renamed it Connecting Theory and Observations. And so basically what I want to show you is, so simulating the baryons from first principle is really, really hard. So what we do a lot, and which is kind of nice, is just take the gravity-only simulations and do something in post-processing on top. And this is kind of like the topic of my talk, like what all can we do if we have this backbone to make our simulations look like the universe at least. And before I start, I do want to give a big thanks to the organizers. It was really, really, really a very nice week. I learned a lot from all of you, and you will see that during this talk. I will mention a lot of your talks during this talk. I definitely ate too much. And I had a really good time and met very nice people. And I thought, so I met Alma, and I have to just tell you this story because 12 years ago, we had a discussion over email about cosmological simulations, and she had some questions about initial conditions from Gadget, and we went back and forth for a few weeks. And this was the first time that we actually met in person, so I thought that was really, really nice. And I definitely, 12 years later, still remembered all our discussions, so it was really nice being here. Okay, so what we want to do is we want to connect theory and observations. So up here you see one of the simulations, the dark matter distribution in the universe, and here you see the galaxies. And so the question is, how do we get from here to here without actually doing hydrodynamic simulations? And I have shown this slide during my very first talk. And basically what I want to say here is, so this is the dark matter simulation. This was done on Titan. And you can do a lot from these simulations. So I mentioned this before, and in this afternoon we will hear a talk by Tommaso about KSZ. You can make maps in the CMB. You can make weak lensing maps. You can make Mark catalogs, and you can make strong lensing images. And so you can do a lot in post-processing on the simulation. And the nice thing is that it's fast, so you can try out a lot of things. So that's really, really helpful. And during this talk, I want to get a little bit at how do we make these Mark catalogs for BOSS, for example, and how do we make these strong lensing images that you see here. So this is usually the slide that I give if I don't have a full hour to talk about this. So this is really kind of like a cartoon version. So what do? We take a big supercomputer, the biggest we can get at, and we do a gravity-only simulation and get the distribution of the dark matter. So then the first thing that we are doing actually is we identify the halos in this simulation, and so you see there's a lot of structure in these halos. So that's the first step. Then we make the assumption that the galaxies, the gas, the light traces the mass, to very crude first approximation. And so we are trying to basically take this information and therefore populate these peaks with galaxies. And yesterday you heard a talk about abundance matching. That's one very nice method. I'm coming back to that a little bit that you can do. And hopefully the population, the prescription to populate the dark matter simulation is independent of cosmology. This is, of course, again, just an approximation. It's not really, really the case. And this question was also asked yesterday. And then on the other side, here we are coming from the telescope. So here I have the Sloan Digital Sky Survey. I measure the distribution of the galaxies. And I try to inform my prescription, how I populate the galaxies on the dark matter from these observations. So what you see here is actually a plot that Martin White made quite a while ago. And so you see the dark points here, the black points are the measurements from the Sloan Digital Sky Survey. The red curve is if I would just calculate the two-point correlation function directly from the dark matter distribution. So you see it's falling a little bit short, and that's because of the galaxy bias. So I have to do something about that. And then the blue curve is if I take a prescription and really populate the dark matter simulation with these galaxies. And so you see this works really, really beautifully. But you also see immediately that there's a little bit of a drawback because I had a very specific set of galaxies here. In this case, it was the luminous red galaxies. So this prescription is very much depending on what kind of galaxies I'm looking at. The other problem that we will have is that this is a picture. This is just the same SDSS picture from up here, just a little bit bigger. And this is a picture what LSST will see in exactly the same patch of the sky. So this was made with a deep lens survey, which is a telescope that basically has the same resolution as LSST will have. And so you see that you have many, many, many more galaxies, much more resolution. And populating these simulations with galaxies will become ever harder. The other problem is that these error bars will become much, much smaller. Remember, we want to figure out what dark energy is, and we want to get the correlation function down to a % level accuracy. So getting these prescriptions to work will become a bigger challenge in the future. So just as an easy introduction to halos, so right now, if we have the dark matter simulation, there are two more or less popular methods of finding the halos. So one is the friends of friends methods, and I'll explain this a little bit more, and the other one is the spherical overdensity. And Martin White wrote in 2001 a very nice paper where he contrasts these two methods. One of our students at that time, now he's a staff member at LBL, Zarya Lukic, for his thesis, he tried to come up with nice connections. If you have measured one halo mass in a simulation, how do you get to the other description? And you can do that if the halo is nice and relaxed, but not if the halo just underwent a major merger or something like that. And so let's just go through this. So how do we find a friends of friends halo in the simulation? I go to a particle, and let's say I start with this particle, and I ask who is in my neighborhood within a certain linking length. And so this linking length is often, it is always defined with respect to the average interparticle spacing. And it's set very often between 0.7 and 0.2. And so then you go and you ask who else is in my neighborhood at this linking length. So I find all these particles. Then I go to these particles who are my friend and ask, who are your friends? So this guy already found a friend up here. So he belongs to my halo too. And then this guy, and this guy, and this guy. And the other guys are too far away, so they don't belong to me. So this is my friends of friends halo. So one thing that you can do is now you can ask, like, I could also redefine this thing and say I only take people who actually have two friends, right? So I could say, like, okay, this guy belongs to my halo because he has 5 friends. And this guy, these two guys, this guy belongs to it because they have 2 friends, but these guys don't have any extra friends. So I actually take them out. So what happens, so this is called dB scan, if you look it up in the literature. So you get slightly tighter halos. Some people are worried what happens if there's a particle close by just by accident, and this particle is connected to another big halo, so they call this bridging. Then this could be an unphysical thing. So I would, like, if I use this dB scan algorithm, I would avoid having these unnatural bridges. The other thing that people very often do is they use the overdensity. So what you do there is you go into your simulation and you find the high density peaks, and here you see the Santa Barbara cluster, which was a cluster that we actually discussed 12 years ago. And so you see here a high density point is in the middle here. So you draw a sphere around this guy, and you measure what is the density in the sphere with respect to the background density. And if it is above a certain value, often it's 200, then you start and say, yeah, okay, you belong to my halo. So you build up this overdensity contour here. And if you remember Buvnesh's talk, he said halos are spheres. But as you can see, I mean, this is a halo from a simulation. They are definitely not spheres, right? So the problem with the overdensity is that you actually impose geometry on the sky that is not really, really right. The other thing that you should keep in mind when you try to decide what halo definition you should use in your simulation is it depends a lot on your observation. So if you look at X-ray observations, for example, where people measure the gas temperature and so on and so forth, they very often stay very close to the core of the halo, and so there a spherical overdensity makes a lot of sense. But if you look at, for example, weak lensing mass measurements, they really try to get the contour of the halo correctly, and then you really trace much more what the FOF halo finder shows you. So neither of these definitions are perfect, but you should just make sure that you find the right one. And this is just an example where I took a halo out of a simulation and I colored it with respect to the different definitions. So the green guys are just all the particles in the simulation. The blue guys are the particles that were found by the FOF finder. And this black contour is just an isodensity contour that I put on top of it. So you can see it traces quite nicely what the FOF finder finds. And this red guy is an overdensity of M200. So you see that these masses are quite a bit different. And as I said, there are papers about like how do you connect these two masses in a mathematical way. Anyway, so yeah.
So on that slide, would you say one of those methods was better than the other for that particular halo?
For that one?
Yeah.
I personally, and this always seems to be a fight between people, I personally prefer the FOF halos because they really get much more the structure of the halos correctly. But other people would say this overlinking problem that you have pieces that might not quite belong to the halo that really bothers them, so they prefer the SO halo. Which one is your preferred? You're like me. That's great, yeah. Right, but if you ask Risa Wexler, every time I tell her we found FOF halos, she said, oh, that's totally wrong, but it's not wrong. So, so here we have some more examples just for fun. This is also from the Lukic et al. Paper where I show you, so in green you see the SO halo, and in white you see what the FOF finder found. And what you can't see is that the white particles are also underneath the green particles. So in this case, we have this nice spherical, relaxed guy who formed early on in the simulation and nothing much happened to him. And so you see no real difference between them. And here you also see, in this case, when I plot the density profile for this guy, so we heard a lot about density profiles in the last few days, it's very nice. So what you do is you measure again the density in spheres and you plot it up against the radius, and you can fit something very nicely to it. Down here what you see is this overlinking problem that I described, and you can also get rid of this a little bit by making the linking length smaller. But you see that there are some bridge particles, so the FOF finder actually thought that there is a big second component here. So then down here what you have is a halo which is a very active halo, so he has a lot of, or she has a lot of substructure here, and so now if you try and actually impose a sphere on it and try to put a profile through it, so you see it doesn't really work, right? So these blue guys are the measured density in these spherical shells, and so you see if I try to put an NFW profile through it, I really force it, this halo then gets a very, very low unphysical concentration. So this just shows you that you have to be careful. The other thing that we will use in order to populate the halos with galaxies are the subhalos. And so here you see a halo from, again, the Q-continuum simulation. So the Q-continuum simulation has pretty high mass resolution. It's a particle has a mass of 10 to the 8. And this halo is a very healthy halo of mass of 10 to the 14. And I actually gave him a name. His name is Albert because all the observers always name their clusters, so I thought the simulator should start this too. And actually, with our students, they very often look at the same halo over and over again, so we needed a naming convention. And so what you see here is what we did was we ran a subhalo finder on a static snapshot. So we really started and went into this halo and use something like a hierarchical friends of friends finder within this halo. What you have to be sure is that you don't get spurious subhalos, so you want to make sure that you also take the velocities into account. You want to make sure that these little guys are actually bound. It turns out if you just do all of this from a static snapshot, it's actually not so easy. What you really want to do is you want to take into account the time evolution. So you want to see, like these small, like this guy here, for example, this halo was probably a halo by itself at an earlier time snapshot and just moved into this halo and now has become a subhalo. But he also might move out again. So you really want to take into account the dynamics of the system as well. And so you can make these subhalo finders pretty complicated. And actually, I forgot to mention on the previous page that there's a comparison of different halo finders. Paper was led by Alexander Knebel. And if you look up Alexander Knebel's papers, he does a lot of comparison projects. So whatever you can get out of a simulation, he and his team is going to compare to something. So this Onions et al. Paper is about comparing subhalo finder implementations. So they have a large number, more than 10 subhalo finders, and they see how they actually get different structures. And if you take a look at that paper, you'll see it's not an easy task. So now let's see what we can do if we just identified the halos themselves, so no subhalos. So this is what I showed you before on the slide, on this overview slide, how we connect the dark matter simulation with the galaxies. This is a very nice and simple way to do that. It's the halo occupation distribution approach, the HOD approach. And I didn't give you all the papers. There are lots and lots of papers. This idea is out for a long time. But one which I'm giving you here, which I thought was really nice, is the paper by Zheng et al., where they actually applied this to Sloan galaxies. And so here you see basically the basic idea is pretty simple. So you take the halos that you found in your simulation and you just measure their mass. And depending on their mass, you assign galaxies to them. So if you're above a certain mass threshold, and this is this MCAT parameter here, you give this halo a central galaxy, just one. And so you can see this here. So this is the number count. So here is this threshold 1. So and this is not a hard cut, right? This is a distribution. So you really have a distribution. So there's a probability that you give somebody a central galaxy. And if you are above another cut, you also get satellite galaxies. And so this is the second cut here. This is this M1. Actually, let's go here. So this is at 10 to the 14.7. So if you are a really big cluster, you get more than one galaxy. And then you distribute these satellite galaxies with respect to an NFW profile. You can be also a little bit more sophisticated and use the subhalos, but the basic HOD model just takes the NFW profile. And so if you do that, depending on the brightness of your galaxy, your parameters change. So this dark set of black parameters here that you see leads to the HOD prescription to this light blue one are the brighter galaxies, and the lighter colors here are the red guys. So you do that, and then you compare this. You tune your parameters that you have here to observations, and in Zheng et al. They did that. And so here you get your correlation function, and you see this fits actually quite nicely. So the red line is the theoretical prediction, and the red points are the measurements from Sloan for these two galaxy populations. And the other thing that they have shown here is also the halo model, but I don't want to talk about that today. And so once you have this prescription, you can do a lot of things and make things really look like the survey. So you have seen a lot of BOSS survey pictures in the last few days. So this is the DR10, but this is actually from a simulation. So Shirley took one of these mock catalogs. She took the prescription that is provided for the HOD from the BOSS people, and then she used something which is called Mock Factory, and it's software written by White, Tinker, and McBride, and it's publicly available. And it helps you to actually put the actual mask of the survey on top of the simulations. So if I would have shown you the mark catalog just from the simulation, it would have been filled out everywhere, right? But we want to mimic something that really looks like the data, so we want to put the mask on it and then really make it look like the survey. Here's another one that Martin White actually put on top of one of our larger simulations, and this is for DESI. And so as I said before, it always depends on what kind of galaxies you want to mock up. So this one is for the LRGs that DESI might see, and there's another one that is for the ELGs. So they have different prescriptions. So the thing about HODs is that they are simple to implement, but they are obviously not predictive. So now let's go, what else can we do? Again, we just have the halos and the subhalo information. What else can we do to make things look like our universe? So one of these is a simulation and one of these is observations. Can people guess? Who thinks that the left side is, let's say the left side is the observation? Only one person, two people. And who thinks the right side is the observation? Let's see. Yeah, so most people were right. So this is something that Nan Lee, one of our postdocs, and Mike Letters at the University of Chicago have worked on a lot, and also Steve Rangel, who is a student with us, and Lindsay Bleem. So the thing is, if you know these people, the interesting thing is, so Lindsay is an observer, Mike Florian is a student at U Chicago, is an observer, Salman is a simulator or theorist, Mike is an observer, Nan is somewhere in between, Steve is actually a computer scientist, and I'm also more a theorist. So you see that there's this combination of theorists and observers that you really, really need in order to make things look like the real universe. So what did we do here? So first of all, so this is, what you see here is, what you should have picked out is a strong lensing arc here, right? So this is something that we want to do in order to produce strong lensing images from simulations. And so you have seen something like this before in Bovnesh's talk, just to remind you concept of strong lensing. So here you are sitting on planet Earth and observing the universe. And up here is a lensing source, and here is a big warping lens. And so what strong lensing does is it bends the light from this lensing source, and you get these very beautiful arcs in the image of the lens itself. And so we heard yesterday a talk, you can do a lot of physics with these measurements of these arcs. So people do that. And so what can we learn from strong lensing? And as I said yesterday, we had Juan's talk, who took a cluster A1689 and told us a little bit about dark energy constraints here. So that's one thing. You can actually just take one of these lensing systems and get physics out of it. But another thing that you can do is you can count how many arcs actually do you find on the sky. And Bartelmann et al. In 1998 actually did this. They had a very small observational data set, and they said if we take this observational data set and we extrapolate how many arcs we should find in the universe, they said it should be somewhere between 1,500 and 2,300 arcs. Then they said, okay, we go to the simulation and we simulate a lot of different, so remember this is 1998, right, so a long time ago. We simulate different universes. So we simulate an open universe, simulate a lambda CDM universe. So SCDM, for people who don't remember, this stands for standard CDM, so that was a Hubble of 0.5 and no dark energy. And so that was a standard CDM. And so they did these simulations and they found that actually the open universe is the closest to what they would extrapolate from their observations. And so immediately there was a question, is this a crisis for lambda CDM? And of course it's not. So the question is, how did they select these few arcs that they actually found? And what is the distribution of the sources that they actually look at? And so there were lots and lots of questions on the observational side. I mean, this number here just didn't seem to be right. And you can also do other things than just counting them. You can look at the ratios of the radial to tangential arcs. You can look at double images, quad images, and so on. You can also get properties of the dark matter out of these strong lensing images. And you can look at the dark matter halo profile. As I said, we heard this short talk yesterday, which was very nice, showing what all you can do. So these are definitely interesting systems. And so this is now a little bit of a, since it's Friday, we are all tired, I just wanted to show you some pretty pictures. This is actually something that Mike Gladders gave us. So what Mike did was he looked for strong lenses in the SDSS survey. And he found a set of nice images, arcs, roughly 400. And so here you see a snapshot from these, right? So you see here you have almost the full Einstein ring, very nice. Here you see very strongly you can make out the arcs. And so one question that Mike always has is, so I have all these images in the Sloan survey, how do I find the arcs? And so what he does is he actually has a human supercomputer, which is his students. And and I must say, he also does this. But basically what he does is the following. So he takes these pictures that he gets from the Sloan survey, and he hands a whole bunch, thousands of these images, he hands to 3 students. And every student has to look at these images, and as I said, he does it himself as well. He said when he's bored on flights, he does that. And you have to say, yes, there is an arc, no, there is no arc, and maybe there is an arc. And the other thing that he does is that he shows you this picture, for example, not only once, but he also rotates it and shows it to you again and see if you say the same thing both times or not. And so he actually found that they got a very complete sample of arcs from the SDSS survey. So it worked out extremely well. A lot of people have tried to come up with learning algorithms to have the computer do this automatically for you, and it turns out it's really, really hard. The human eye connected to the brain is very good at getting these features very, very fast, but these machine learning algorithms actually have a pretty hard time. Anyway, so he came up with this set of 400 lenses from the Sloan survey, and then he did follow-up observation with the Hubble Space Telescope on this. And as I said, it's Friday, so I just want to show you some pretty pictures. So now you see really he has these beautiful images with very high resolution. Here you see the arc. Here's another one. So you see pictures. This one is also a very beautiful one. So you see the arc here. And it's very interesting if you ever get the chance to sit down with Mike and look at this. He has so much information just looking at these pictures. I mean, I just look at it and I say, yeah, it's beautiful, and I see the arc. But he immediately has like physics interpretation that, like you see here, there are actually 3 pieces to this, right? If you look carefully. And so he's getting very excited when he does this. It's really very nice. So as I said, just pretty pictures. Here, this one is also very interesting, right? You have here this very large structure down here. Another one, very impressive. So now what Mike wanted to do was he actually wanted to be a little bit more controlled about how you find these arcs, and he said, why don't we take a big simulation and we produce these arcs and we see if we do the selection process again, how well do we do? And so this was Nan Lee's task, and here is the first piece of how do you get this lensed image out of the simulation. And it's a combination of data as well as numerical code. And so every time you see something in green, data is involved, real data, or simulation data. So Nan also calls it simulation data. Blue is that he had to write some code, had to do something. And purple in this case is the output. And this is just a connector which can be an equation or something like that. So we took the images from the Hubble Ultra Deep Field and we used them as the background sources, right? Because you need something that you want to lens. And the halo, so we identified all the halos with their substructure in the simulation. So we used here this the outer rim simulation, which is a 3 gigaparsec box with a mass resolution of 10 to the 9. So we have a very large number of big clusters with very, very good resolution. And so we identified all these halos. And the first thing is you do a density estimation on them. And this was what Steve Rangel did. And the slightly tricky part here is that if you want to get the density estimation, remember in the very first lecture I told you you can just put a regular grid on this, but if you do that, you can run into a few problems if you want to get high resolution. Suppose you take your grid and you just overlay it on the particle distribution and you make it very, very fine. So in some of these cells, if you make them very, very fine, there will be no particle. So that's a problem because then you get garbage, right? Because you have a zero there in your cell, so you can't do that. If you make your grid too coarse, then you don't get the resolution. So you use actually more sophisticated algorithm where you try, so they are triangulation algorithms, where you try to come up with a way that you always have a particle in your cell, but that the cell size is in such a way that it also takes care of that it's not too large if you have a lot of resolution in your simulation. Anyway, so Steve implemented this. It's a very fast algorithm, and it works very nicely. So Steve takes the halos that I'm giving to him from the simulation, and he gets a density estimation. And then Nan takes them, puts the source galaxies behind it, and does a ray tracing through this big cluster. And then he gets a lensed image. And this is how it looks like. So these are the arcs that he produces. But so that's not all that you saw in these pretty pictures, right? The other thing that we want is we want to populate the big cluster from the simulation with cluster galaxies. So the next question is, how do we do that? So Mike Ladders has carried out in the past something called the RCS2 survey. So this is a cluster survey that was done on the Blanco 4-meter telescope in Chile, actually. And from that, he has a very good idea how the members of clusters, the galaxies that live in clusters, look like. And so again, now we go to the outer rim simulation. I told you we have identified not only the halo to make the arc, but also the subhalos in this in all of these halos. And we measure from the subhalos their masses, positions, shapes, and orientation. And then we heard yesterday this very nice talk about abundance matching. So we use this idea to take the galaxies from the surveys to populate them into this big cluster. So basically, we look at the observations, so this is real data. We rank order the galaxies that we have in these clusters by their luminosity, and we rank order these guys by their mass. And then we say, okay, the biggest subhalo should get the brightest galaxy, the next biggest subhalo should get the next brightest galaxies, and so on and so forth. And so we do that, we put this all together, and so this is how it looks like. So now the arc has gone away for a second, but this is what happens if you take a halo like Albert and you populate the subhalos with galaxies that look like the observations. So now we also need the line of sight galaxies, right? We have the big cluster, we have the arcs, and we also need, because I'm sitting here on Earth and the cluster is far away, I need to know how the line of sight galaxies look like. And so again, we are using real data from the Hubble Ultra Deep Field in this case, and we put the line of sight galaxies into this image. And so this is how it looks like. And now we can put all of these images on top of each other. So here you saw, so these were my line of sight galaxies. Now you see I put the arcs. So these are the arcs from the start. And I also put the member galaxies of the cluster on top. And then I'm saying, like, my telescope is not actually as good as my simulation. So depending on the telescope that I have, this I think was for the Magellan telescope, I smear out my observations. And then I can also put the stars on top. I haven't included that picture yet. But so you can see, you can mimic different telescopes. And if you look into the paper that we just recently put on the archive, Nan Li et al., he actually, together with Mike Ladders, mocked up 3 different telescopes. And so now you can really start and give these images to your students and see if they actually identify the arcs correctly. So now in the next piece of this talk, I want to go and talk a little bit about what else you can take into account. So right now what we have done is we took a static snapshot, we identified halos and subhalos, and we got some information out of that. But you can also take, of course, a time evolution into account. And so what you see here is a merger tree from one of the simulations. And so each of these little ellipses is a halo. So this is a halo that comes out today. So this is at redshift z of 0. And this is how it built up the halo over time. The colors are in this light purple are light halos, and the bluer you get, the heavier you actually get. And so you can see the evolution of this halo today is really rather complicated. So lots of things happen to that halo. Here's a big merger that you might not see from the back, but basically 5 halos got together here to form a bigger one. And you can imagine that this will influence a lot what kind of galaxies live inside me. So if my history is very relaxed and nothing much happened to me, I am very old, then I most likely have red galaxies inside me. If my history is very violent, I am very young, then I probably have blue galaxies inside me. So you can actually use this information, this dynamical information on how the halo formed to actually make a better guess of what galaxies will live inside it, and we'll come back to that. Here you see another merger tree, and this time it's shown actually in a spatial way as well as in a time way. So you see here these big circles are backbones, the backbone of the merger tree. So the backbone is what we call like the heaviest piece of that halo. And so you see again, it's pretty complicated. And so you see that a halo today, so this is the halo today, forms from a region that's roughly 5-ish megaparsec big here. So it's actually not that big, which is quite nice. So the halo doesn't form from things that come from all over the box. And so again, Steve Rangel worked a lot on this, and there's a lot of literature out there. And I don't know if I mentioned this on the next one, but Knebe et al. Again compared in detail different merger tree codes. And so there's a lot of things that can happen in your simulation that you naively don't really think about. And so here's an example. Suppose here we are at a time step, some time step 1, right, and we have 2 halos. These 2 halos start traveling, and they come quite close to each other. So at this time step 2, they actually overlapped a little bit, and any halo finder will find them as actually being one halo. But they were just traveling in this way, and in the next time step, they are already separated again. And so if you would look at this naively without knowing what the history of this thing is, this guy would pop out of the blue, right? Because when you do a merger tree and you only look at the previous time step, so you would find one halo here, and in the next time step you would say, well, this is my child halo because he has most of the mass of the system, even though he lost a lot of mass, so you might be puzzled about that. But this guy doesn't even, since he has not enough mass from the system, you would say like, oh, he just came into being. And that's obviously not right because he actually existed already over here. So what you really want to do is you want to be very careful, and you want to take some memory, you want to include some memory of the formation of halos, and you want to try to entangle them and really say, okay, these 2 halos, they lived by themselves really like that. And so what Steve did here is he wanted to see if he can actually come up with a plot that describes this a little bit. And just let me spend a minute or two on this plot. So what he has done here is he took a time step and identified every halo, and he took the previous time step and he identified who was my progenitor in this previous time step. And suppose every particle would be in a halo, then I should be able to say, if I take my mass and I subtract my progenitors and I divide by my mass, everybody should end up here at 0 because every particle is in a halo, so I should be able from one time step to the next to say who are all my progenitors. So everybody should line up on this line. But it turns out not everybody is actually in a halo because my mass resolution is not finite, right? When I find a halo, I have to say, for example, when I use the FOF finder, I have to say, okay, what is the smallest number of particles that defines a halo? So I can say it's, for example, 10, right? Everybody who has less than 10 particles, I don't consider a halo. But now, if I'm a big halo, I could eat up the structure that has 9 particles that I'm not calling a halo, so I would not include it in this progenitor sum, but I'm still eating it up, so I'm getting heavier without having this progenitor mass included here. So what would happen is I end up in this part of the plot. Or what could happen is that I'm losing some particles, right? Something happened to me, I got disturbed a little bit, but it's not enough particles. I'm losing 9 particles. So these 9 particles will float now by themselves in my simulation. So actually, I would not identify them as a halo in the next time snapshot. And so these are these guys. So these guys lost some mass. So somebody stole my mass or something like that happened. And so they end up down here. And these lines that Steve actually drew is, so this line is the line if somebody lost less than 9 particles, because the 10 particle limit was a threshold here. This one is if somebody lost 2 halos at least, 2 halos below the threshold. And this one is 3. So you see that there are these outlier cases where you actually have this thing happening that you eat or you lose a halo which is below the critical mass that it's identified as a halo, and so you end up here. So if you do not take into account a lot of these difficult cases, and again, there's lots of literature, people have thought about this quite a bit, but if you naively implement a halo a merger tree code, what you'll find is that this plot is populated with a lot of junk. And so you have to be very careful about that. Another consistency check is that you can measure the length of a tree. So you can measure so we started identifying halos at 10, and we went all the way down to 0, and you can measure at how many, when was a tree actually born and how many time steps did it survive. So that's what we call the length of the tree. And what you should find here is actually that if you're a very heavy guy, there shouldn't be any new heavy guys later on, because if you have a mass of 10 to the 13, 10 to the 14, so these different colors are actually different mass bins. So if you're very heavy, you should have formed early on. You should not have popped into existence later on. It's just from the structure formation picture that we heard about in the previous lectures, it's just not possible. So this is also a nice consistency check. And here, as I said, again, we have Knebe et al. So they always change the lead author on these papers, but they also did a merger tree comparison. So you see here, there are different merger tree implementations. And so down here, you see the heavy halos, and so you see these guys are actually having some halos that pop into life later on. And these are the heavy bursts that I showed on the previous slide. So you have to be kind of careful about these things. So now in the last, which time do I have left? Yeah, in the last 5 to 10 minutes, this is a nice example that I actually borrowed from Heitmann and Watson. So now we have not only the halo and subhalo information, but we also have this merger tree information, so we know what happened to a halo over its lifetime. And I can use that to actually make more catalogs. And so Heitmann and Watson had this very nice idea to take into account the age distribution of halos. And so what do? They calculate for each halo in the simulation this Vmax, and we heard about that in Yao Yuan's talk yesterday already. So he introduced the abundance matching for us. So you calculate Vmax for each and every halo. So you look at the mass distribution with respect to the radius and the velocity distribution here. And they also determined something that is called what they call Z-star. And I copied that out of their paper so that I don't forget what they did exactly. So they calculate different redshifts that are connected to the formation history of the halo. So one of them is Z characteristic. So this is the first time that actually the halo exceeds a mass of 10 to the 12. So this is kind of like with the HOD. Remember, we had this mass cut that somebody shouldn't have a galaxy if the halo is too light. So this is the first redshift that they calculate. Then the next one is what they call Z accretion, which is if you have a subhalo, sometimes you get in and out of the halo. So you become your own halo again if you get outside of the halo. And so this Z accretion is what they call once a subhalo really remains as a subhalo. So if you are the big host halo, your Z accretion is 0. So this is the next one. And then they calculate Z form. And so this is a little bit of a complicated description, but basically it's based on a paper by Risa Wechsler et al. From 2002, and they look at the redshift at which the halo transitions from fast to slow accreting. And this information, again, you can get out of the merger trees. So they calculate for each halo all of these 3 characteristic numbers, and the biggest one of them they call Z star. And so Z star is the redshift at which the star formation in a galaxy ceases. So if you have a larger value of Z star, you are older, and so you become redder. Then the other thing that they are doing actually is, so they go into the simulation, and so they are using the Bolshoi simulation. We have heard about the Bolshoi simulation yesterday. It's a 250 megaparsec box with 10 to the 8 very high mass resolution, and they calculate V peak and Z star for each halo and subhalo. Then they assign a luminosity to each of these subhalos using the abundance matching technique. So we have heard about that yesterday, so you're all familiar with that. And then the second thing that they are doing is they're actually using this Z star distribution to assign a color to each halo. So what they're saying is we rank order these Mark galaxies. We bin them in luminosity, and then we assign a color to them. We rank order them with respect to luminosity bins, and then look at the Z star. So you put all of this together, and you compare it to observations. So this is, again, observations from Sloan. So this is from Zehavi et al. And you actually get very nice agreement. So this is the luminosities that they get from the abundance matching. And these are the colors that they actually get when they take into account the Z star. So what I only want to show you with this, so you should all read this paper. I think it's a really nice, cool idea. That with a little bit of information, so they only have 2 numbers for each halo, but that tells you a lot about the galaxies that live in these halos. And you can do a lot of things if you take into account not only the properties of the halo at a static time snapshot, but also you look at the history, what they have done. So semi-analytic models. So I really don't want to get into this, and the reason is that actually Claudia did a really good job, so she looks a little puzzled. So the nice thing about semi-analytic models is that you get a lot more information. So previously what we saw, we got luminosities, we got colors, but the semi-analytic models have a ton of physics on top of it. And so what they are trying to do is, again, they are trying to take into account the formation history of the halo in detail and the subhalos. And then you have a whole bunch of physics parameters, and you probably can't read them, but that's okay. And this list goes on quite far down here. And because you put in all of this physics, you also get a lot of information out from the galaxies. So here you see we have a luminosity plot, and the green guys are actually this case I picked Galacticus from Andrew Benson. You could have picked another Sam if you wanted to. So the green guys are the prediction from the simulation and the semi-analytic model on top. The red guys are the data, so that looks pretty good. But you also get things like the galaxy bulge stellar mass versus the supermassive black hole mass. So you get really a lot of physics out of this. The problem with the semi-analytic models is because they are so complicated, it's also not so easy to tune them in a way that they actually give you always the right answer for everything. But it's very, very interesting approach. And you should ask Claudia all about it. This is just a cartoonish way. So what do? You put all together what I told you in the last 50 minutes. You take your simulation, you find the halos, you build the merger trees, you put Galacticus on top. So here you might see there are actually little galaxies in here in these halos. So you put it all together and you get a catalog of galaxies with a lot of information. And just to summarize, so what I wanted to show you today was not actually how you simulate the model, the baryons in hydrodynamic simulation, but rather what you can all do if you have a high quality gravity only simulation and you model the galaxies on top of that. So the advantage of it is that you can try out a lot of methods. You can put in a lot of information or little information. I forgot to say also that in the talk yesterday we heard that the concentration of the halo tells you a little bit about the galaxies that live inside it. So you can try out a lot of things, and it's relatively fast compared to doing a full hydrodynamic simulation. The HOD approach is very popular for building more catalogs for LRGs, for SDSS and BOSS, for example. And the nice thing about this one is that you only need a moderate mass resolution, so you don't have to kill yourself because you don't necessarily need the subhalos. And the parameters are set by matching to observations, so this is one approach. Then we have the subhalo abundance matching. We heard about that yesterday. Lots of papers also there. For example, Conroy et al. In 2006 is a very nice description. Here it's a little bit more demanding because you need high mass resolution because you actually want to resolve the subhalos within the simulations. Then I just told you on this one slide about the conditional abundance matching. So actually the merger tree information is also included here in the sham. So, but here there was this very nice idea of how you can actually get also the color information. Again, you can also get this here, but I just thought the way how they approached it was really elegant and nice. And then down here you have the semi-analytic models, and so they have everything in it that you can dream of. They have star formation models, feedback, gas cooling, so it's a zoo of parameters, but so you get a lot of information about the galaxies, and in principle, you can also get answers at unobserved redshift. So all of these methods are actually always tuned. The parameters here are tuned to observations. And the one thing that you want to get for LSST, for example, is you want to get into a regime where we actually don't have the observations. So in principle, the SAMs are predictive, so that's very, very nice. That's the big advantage of them. But then they are also pretty complicated. And that's it. Thanks.
Questions for Katrin?
So I think there are some prospects to measure the amount of substructure with strong lensing.
Mm-hmm.
So in your simulations, do you think that, I mean, from what you have learned from simulation, do you think that will be feasible?
So there is one worry that, so yes, we are hoping that, and we are trying to do that. And there's also some discussion with people who do the reconstruction, right, of the mass field on observations to try it out on the simulations. But there's one worry that people always have is that at these very small scales, the baryons do become important, right? So if you would have the baryons in the simulation, they might alter the distribution of the dark matter inside the substructures. So there's a little bit worry about that. If, because we are neglecting the baryons, we are doing something wrong. But so this is something we definitely want to look more into, like how much can you get from the dark matter only in this case.
More questions? Let me ask one quickly. So you subtitled this Connecting the Theory to the Observations. So how much can we learn if we know, for example, the distribution of concentrations in particular types of galaxies, or if we know something about the halo occupation distribution, what does that tell us about the underlying theory of the universe?
So right, so I think you, so now we are talking more about the theory of the galaxies, right? Not so much the cosmology. And I think you can learn actually quite a bit, like this example of Heitmann and Watson. It actually tells you a little bit about galaxy formation physics, right? If you get the colors right, when you take into account more properties of the dark matter halo, right? Or when you take the concentration into account, for example, if you have, so if you are an old halo that nothing much happened to it, your concentration definitely will be higher, right? And so therefore your galaxies will be different. So I think you can learn you can get a lot of intuition from that, like what are the properties of the halo that actually connect to the galaxy population.
Yeah. I wanted to ask, how far are we to have simulations in which you have baryons from the very beginning and that you let them to evolve and instead of populating halos with.
So actually you should ask Tiziana that question because she's much more an expert on this than I am. So the problem is that the simulations where you have the baryons from the start, they are roughly a factor of 10 more expensive. And they also have to have very, very high resolution in order to resolve all the physics that is important. If you don't have the high resolution, you will get probably some garbage. And there are a lot of comparisons of the dark matter only versus the hydro. And I see that Tiziana has a microphone, so she can actually say a little bit more about this.
I mean, we are at the stage where we can start doing those kind of simulations in terms of, the algorithms being, decent enough, and the computer power that we have is that we can run these full-blown calculations with full hydro and star formation model and AGN models. But as Katrin said, something has to give, right? So those can only be run in smaller volumes. They're still cosmological representative volumes, like up to maybe the best ones sort of at around 100 megaparsec, which would have enough resolution at which the physics that you're trying to add actually has some meaningful predictions. There's still a lot of work, particularly at lower redshifts, where feedback processes are coming in order to form the galaxies that we do see. So there's still a lot of work, but I'm very optimistic because there's been a lot of progress. There have been runs like the Eagle run, the Illustrious simulation one that we did, Massive Black 2. Those are all came out last year, and I think made a lot of new breakthroughs in terms of getting a galaxy population that is starting to look closer and closer. Even the first predictions that that we're actually showing from this, the first predictions in comparison with data in terms of luminosity functions of galaxies, mass functions, and so on. People didn't even dare to go there until this last sort of generation of simulations because it wasn't really. So we are definitely making a lot of progress. So there's a lot going on in that. That's another, so the blue tide simulation is another very large volume, that's sort of a pathfinder for this, volumes as large as the largest dark matter runs that have been run, but that simulation is only run to very high redshift. Yeah, so that's another thing. So for, as Katrin was saying, they're so demanding in terms of computational power that when you try and match a very large volume similar to, say, the ones that we've been, Katrin has been talking about in dark matter sector regime, then you will never have the computational power to run into redshift 0. So, but yeah, so this is the start of this, and I think the future is bright. We are really getting to do this now, and I'm sure Katrin will do some of it herself soon enough.
If you're using these for parameter estimation, how do you break the degeneracy between the cosmological parameters and your tuning parameters?
That's a very good question. There are some papers out there by David Weinberg's group, for example, where they actually look into the degeneracies between HOD parameters and cosmological parameters. And some work has gone into that, but yeah, it's something. Right now the error bars are still big enough that it's not such a big problem, but it's a good question, and it's being worked on.
Okay, let's thank Katrin again.